here on our next slide, we can see the continuous function, which is the solution to the previous model, namely a function that, as we have seen in the beginning, is something that has time in it. So the t is actually also there as we had it before, except now it's not a simple linear function of time, now it's an exponential function of the time. So how do we calculate it? The n of t on the left-hand side of this equation can be calculating as a constant n naught multiplied with the exponent of a factor called k times this time that we had, and have it expressed here as this lowercase t in the parentheses. So we can have a continuous function which is defined for any value of t, so it can be any rational value, so it can be fractions also, and whatever we like to put in, not only integers as we have done it so far, but for just any value. This is a continuous function, and we could actually try to fit the previous model with its specific population starting size and its population growth rate, which was expressed as 1 plus r, by this continuous function. And if you look into the materials, it says here explicitly how to calculate the constant k that we need in this function from the fractional growth that was previously 1 plus r. And it's done here in our slide. We have it at the bottom defined here. K is calculated easily from the fractional growth as the logarithm of 1 plus r. So with this knowledge and the information that our starting population, namely when time is equal to 0, the whole factor on the right of this, on the right-hand side here, will be equal to 1. So we'll start with n naught. So this is our initial starting population, which needs to have a numerical value in MATLAB in order to do it. So let's see how we can define this function and how we can superimpose it.
Okay, so I'm going to use the same file that we've been using previously. Let's just give myself space at the bottom so I'm not typing near the bottom of the screen. You shouldn't be scared of having relatively lengthy files, script files, as long as they're well commented. Probably better commented than I've done today if you want to come back and use them later. MATLAB lets us also divide things into sections by doing percentage sign, so that's what I'm going to do today. Because we're going to look at plotting the continuous function on this same plot. So let's have a new title, continuous function, and let's remind ourselves of the function we're going to plot. So that's going to be, the function is going to be equal to n naught times by the exponential of k times t. Okay, so as we're continuing the plot we had before, I want to do hold on. Okay. Next, I want to calculate k, exactly as Gerald just showed you. K is equal to log, so that's the natural logarithm in MATLAB is given by log of r plus 1. We know what our initial population is, and we want to set that equal to the same number as we used previously. So n naught, n sub 0, a new variable, is equal to n1, which is the previous starting population. So if you look back at our previous script,
see where we have this. Yeah, I have it in line 14 of this code. It's the first population in that vector called n is 100, so we can use this and define this as our starting population in the continuous function as well.
So n sub 0 will be equal to 100 as well. So now we need to define the function. Again, an anonymous function for the explicit solution. So our function, again we use this at sign with brackets. We've got one variable in the function that we're interested in at the moment, t. We could also set k and set n naught, but I think we'll set those equal to the values that we know.
Mm-hmm.
So we're just setting t on each run of this function. Actually, the thing we haven't mentioned so far, and the quite clever thing, is we can just set n naught inside our function. And now MATLAB will go away and find the value of n naught set outside the scope of our current line. So n naught here will always be equal to 100, because that's what we set it to previously. Times by the exponential of, again, k will be the k that we've calculated here, times by t. So unless we anything else needs to be inside these brackets. Anything that MATLAB hasn't heard of before needs to be inside these brackets. In this case, it's just t.
Okay, so it will use t as the independent variable, which we just have on our horizontal axis, and n naught and k, it will look up the actual values. So if they are predefined before, there won't be a trouble with it. So they will be assigned the numerical values that we give to them.
If you recall back to what we did before, we need to set the limits for using fplot, and we're going to set them between 0 and nt. And then comes our handy fplot function. So we just need to pass this func, because it's a function of one variable, at sign t. There's only t, so we can just give it fun directly, give it the limits, and we can also say which color we want it. Let's say magenta. That's pink.
That's for the plot.
Yes.
The color of the line that will be displayed.
So because we've done hold on, if I just run this one section, there's a run section command, then we expect just to plot straight over this plot here. So should we run this section?
Okay.
Okay, so we haven't. So you can see I had a bug in my code, undefined function of variable limits, because I called it limit. So I can just change that to limit. Okay. So run section again. Oh, that's better.
Okay, so what do we have now? We have superimposed on the previous discrete updates that we calculated one by one. Now we have the full continuous function in this magenta color. And well, what do we see? It just overlaps nicely. So we have the continuous solution, and we can see that the simulation of the discrete time model follows the solution very nicely.
That's good to know.
Okay, so one thing that you are asked in the assignment, and that we can just do directly while we have it here, is what if we want to know specific features of that function? So we can arbitrarily do something at what time point is the population size 1,000, or at what time point does it reach a population size of 1,000? So just as an arbitrary example, so a specific thing that we are interested in, a specific prediction, when will it be reached? How do we do this when we have these two things, the continuous function and the discrete time model?
Okay, that's it. This is like a good challenge. So our new task is to find when the population is larger than 1,000. Okay. This will be easiest to do using the first lot of data, so the individual plotted data points here, rather than the explicit solution. Although there would be methods to do this using the explicit solution too. But if we're happy with just finding the minute at which the population size is greater than 1,000.
Right.
Is that fair?
Yeah, we can try that first thing. And we might already from the plot, if we look at our plot, we can already guess what we have to expect, namely that if you look at 1,000, that this is somewhere between, say, 60 and 80.
Well, let's make that even clearer. There's a function in MATLAB called line, which will just plot a line on our plot. So we're going to give it the x values and then the y values. So the x is going from 0 to nt, and the y, let's just say let's plot the 1,000 line. Okay, so just a horizontal line at 1,000.
So slowly, let's try to understand what this is doing. So you're giving what coordinates in which order?
So x1, x2, y1, y2. So the first point it plots will be 0, 1,000. So this point here. The second plot it points it and then it will draw a line to nt, which is
120.
1,000.
Okay, so we'll have a horizontal line. And if we do that horizontal line here nicely in the blue color, so in a different color, we can already guess from that line. So yeah, we are somewhere near 70, maybe just below 70. So we have already a guess from that graphical view, but we can have it numerically in the precision that we like. So if we want to have it within a minute, up or down, where are we? How can we do that from our solution that we have?
So if you want to find the minute where this first passes this point, well, we can do comparisons. So I know that n is greater than 1,000 will tell us whether that's true or false for each point. But that's not very useful for what we want to do. But MATLAB does have this function called find. So first of all, we're generating a new vector which says true, 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 or false. So in this case, it's going to be false up until the point where n is greater than 1,000. Then it'll be true for all of these values. So it'll be false for all of these values and true for all of these values. So this n is greater than 1,000. And find will tell us the indices of all of those values.
Yeah. Indices means we will find out which elements of this vector n are larger than 1,000. It doesn't say us how much they are, but it says which value that is. So the minute, right? If I understand correctly, this is then the minutes, because we have calculated it in terms of minutes. It will say us at which minute we'll find values that are larger than 1,000.
So this gives us the index of in the time points. So the best thing to do here now is to let's find the first time point which is greater than 1,000. So let's call that t1,000. Okay, so we know that it's going to be above 1,000. It's going to be the first element. That's fine. But actually, we want to find out. So this is going to give us a number, and the number corresponds to the first element in time points that is greater than 1,000. We'll go. Okay. So let's go through that again. So what we're doing here is we're checking every element in n, which is the blue dots here, to see whether they're greater than 1,000. So for each of these points, it will be false, and for each of these points, it will be true. Find then finds the first number, the first index, where it's true. The next one, it finds all of the ones where it's true. Okay, so it finds the number corresponding to all of these points here.
So we are interested in the first one of all that it finds.
We're interested in the first one, so we ask for the first one. And then we want to know which time point that corresponds to. So we use that index into time points. So I'd suggest you have a little play around with using the find function in order to work out what's going on there. But we'll leave that for you to do at home.
Okay.
So should we see what this value is? So I'm just going to, if I uncomment out this line, and we get back to our main screen, so let's see what happens. Okay, 67.
And what does this mean now? 67 is the minute where we have a value of the population that is already larger than 1,000.
Okay, so somewhere down here. So 67. That looks fairly reasonable.
And how can we find out what exactly the population is at time 67 minutes?
Okay, so
population is in n, right?
Yeah.
In n, so we could actually look at it. How large is that population?
Oh, okay. So it's just n of 67, which is...
Why is it not? Because that's the thing to do with the time equal to 0, right?
yes.
Because time equals 0 is our first value, so we are actually one below.
Yes. So if time equals 0 is equal to... the first point is equal to time equals 0, we want to subtract 1, so we're looking for the next
one more.
One
so
more.
We're actually
Yes.
looking for the next one, so that means we're looking at this time point, but because we have to add the 0th value, then it will be n of 68. And that value is indeed then a bit larger than 1,000, so we can see that between 67 and 68 minutes of that run, which was started with an initial population of 100, we predict this population to cross that barrier of 1,000.
So we can validate this using our explicit solution. In our continuous function section here, we defined fun. So I wonder what would happen if we give this fun. We just say fun of 67. Okay.
And we get the same value. So that's the convenience of defining the continuous function, because for the continuous function, you can also then find it at 66.5 minutes or 66 minutes and 30 seconds. And you can see we're getting closer to this exact value. You can, of course, also calculate the exact time, now the rational time value, for which it is 1,000.